Imagine a massive data center operating at peak capacity, processing millions of requests per second. Then, without warning, a primary server rack goes completely dark. This exact scenario dictates the absolute rule of application design. System data must remain correct and consistent, no matter how extreme the operational stress. Standard read and write operations are built for ideal conditions. When subjected to heavy, unpredictable load, those basic operations fail to protect the data they process. That failure manifests in three distinct ways, forming a triad that threatens every application: data loss, data duplication, and data corruption. A system's true integrity is measured by its architectural capacity to actively repel those three vectors of state failure. To see how this works in practice, we can look at a mobile vocabulary application that tracks user progression over time. The integrity of this app relies entirely on four critical state variables: the user's learning history, their correct answer count, their current progress, and their user settings. This schematic maps the normal operation. The mobile client holds the state locally and then transmits these four specific data modules outward over a network connection to the remote server. But if that network connection falters, the payloads become compromised in transit. Networks, mobile clients, and concurrent user requests are inherently unpredictable. They are actively hostile environments for state preservation. Simple database create, read, update, and delete operations cannot salvage a system operating in these conditions. Explicit engineering interventions are required. Ensuring these four variables survive the journey from the client to the server requires building three distinct, rigorous architectural defense mechanisms. The first failure mode to solve is data loss, which we can isolate by tracking the current progress variable during a sudden offline scenario. In this network flow, a user completes a lesson moving through a subway tunnel. The device attempts to transmit their current progress over a severed connection. Relying on a direct connection means when transmission hits the break, the data drops and is permanently erased. To catch this data, a client-side local cache acts as a safety net. The cache intercepts the blocked transmission, storing it safely on the device. When the network is restored, a background sync automatically pushes that stored payload to the server. Because this handoff happens entirely in the background, the user remains completely unaware that the network ever dropped. Preserving user effort requires abstracting the volatile network layer entirely. The application relies on local persistence queues to guarantee the data eventually reaches the database. The second failure mode is data duplication. We can see how this corrupts the application by looking at the correct answer count variable. This diagram illustrates a client device sending an increment count payload. The server receives it successfully, but the return acknowledgement receipt vanishes midway back to the client. Missing its confirmation receipt, the client assumes a total failure and aggressively retries the exact same request. The server blindly accepts the retry, and the answer count database integer artificially inflates by 2 instead of 1. Blindly trusting the network to reliably deliver single occurrences is a fatal flaw in modern distributed system design.
The architectural solution to this is the item potency key, a unique identifier attached to the payload directly by the client before transmission. Upon receiving the first attempt, the server logs this unique key. When the inevitable duplicate retry arrives, the server recognizes the logged ID and explicitly blocks the redundant payload. Item potency guarantees that the application state mutates exactly once, regardless of how high the retry volume gets. Accurate counting in distributed environments is achieved by mathematically guaranteeing uniqueness at the server boundary. The final failure mode is data corruption, which frequently occurs when user settings are managed across multiple user devices. Managing concurrent updates is like two high-speed trains on parallel tracks, converging and colliding into a single narrow lane at exactly the same time. When multiple clients mutate state concurrently without oversight, systems often default to a logic flaw known as last write wins. We can see this in a race condition, where an older tablet payload and a newer phone payload attempt to update the user's settings simultaneously. Looking at the data flow, because of simple network latency, the older, outdated tablet payload arrives slightly after the newer phone payload, overwriting the more recent data. As a result, the user's settings silently regress to a stale state. This executes a subtle but destructive form of data corruption. The architectural fix for this race condition is optimistic concurrency control.
This is implemented by attaching a sequential version number directly to the state payload. Before authorizing any write, the server checks the payload's version number. If it holds version 2 from the phone, it actively rejects the delayed version 1 from the tablet, protecting the modern state. Maintaining valid application state requires treating every simultaneous update as a direct conflict that demands explicit, versioned resolution. This wide architectural view shows the complete framework built to defend the vocabulary application, a client, network layer, and database, heavily fortified by local caching, item potency filters, and version checks. To prove the architectural holds, we can subject the system to an aggressive stress test, simulating rapid-fire user interactions and hostile network conditions. Under this barrage, users are answering words rapidly, toggling settings across devices simultaneously, and repeatedly dropping offline. The system dynamically processes this chaos. It actively filters out the bad requests and seamlessly queues the dropped data for later transmission. Throughout the simulation, there is a complete absence of state failure. No data is lost, no data is duplicated, or ever corrupted. Engineered architectural defenses effectively transform an unpredictable network into a strictly governed system. Reviewing the final database at the conclusion of the stress test reveals a completely uncorrupted state. The learning history is fully intact, the correct answer count is perfectly accurate, and the user settings are current across all devices. The structural integrity of the application holds firm. True data consistency means treating every state change as a distributed systems problem, ensuring the user's progress remains an immutable source of truth.